PCB Foundations, by Paul Taubman and Sean Kelly. Presented by 9.Connects. Chapter 3. Assembly Overview. 3.1. Introduction. In the last module, the PCB fabrication process was discussed, which is the process of producing a raw PCB. In this module, the PCB assembly refers to the PCB with all the components installed. In the world of PCB manufacturing and design, nothing has changed as dramatically as the assembly of PCBs. This is simply in response to the amazing reductions that have come about in both the silicon size in the component, and the package that houses the component. As the result, assembly equipment has evolved from soldering large through-hole parts using wave soldering techniques, to the reflow soldering processes of surface-mounted devices so small, they need to be reworked under a microscope. This chapter will present an overview of some of the latest assembly processes. It will mainly discuss SMT, surface mount technology, processes, but will include a few through-hole comments along the way. Throughout this chapter, we will use the terms SMT and SMD, surface mount device, interchangeably. SMT refers to the technology used to mount the device, whereas SMD refers to the device itself. Note that the assembly process is where most design projects crash and burn. The term respin is used to describe the process of fixing the issues of the board found in the manufacturing process, and then resubmitting the corrected documentation for another fabrication and assembly effort. The respin effort can range from a minor landing size correction, to a complete component placement modification, and rerouting of the board. Regardless of the severity of the modifications that are necessary, often at least 2 weeks will be lost in making the fixes to the PCB design, sending the new design through fabrication, and then returning it back to assembly. Most of the design mistakes could have been avoided by simply knowing the processes used in the assembly house. 3.2. General Overview. Large printed circuit board assemblies can have thousands of parts on them, and many can be extremely small, and difficult to handle by hand. An 0201 package is only 24 mils by 12 mils in size, which is slightly larger than a flake of pepper. Trying to hand solder these takes incredible skill and patience, not to mention a powerful microscope. In addition to very small packages, many integrated circuits are now housed in very tight-pitched leaded parts in BGAs, ball grid arrays, that cannot be accessed using a soldering iron. Assemblers are now using automated equipment, as much as possible, to handle the assembly. 3.3. Pick and place. Pick and place machines are used to rapidly place components onto the board. Before entering the machine, the raw PCB pads are coated with a solder paste, which is just what the name implies, a mixture of solder and paste. The stickiness of the paste temporarily holds the components once they are placed, and the solder permanently bonds the components later in the process. An additional glue dot may be added to some components, to assist with the adhesion of the component to the board. The pick-and-place machine is typically loaded with the components that are supplied in reels that contain several hundred to thousands of parts per reel, and placed in cartridges that the machine can use to feed to the placement head. The larger machines can handle multiple pick-and-place heads, each dedicated to a board, guided by vision systems. The vision systems can also inspect the parts to be mounted prior to placement. This can reduce the rework effort, if the part leads have been distorted or damaged before presentation to the pick-and-place machine. The cost of these machines can range from low-dollar semi-automatic machines at $30,000 to $50,000, upward to fully automatic machines in the price range of millions of dollars. The machines are rated based on CPH, meaning components per hour. The programming information for these machines comes from the pick-and-place files that are produced by EDA tools. An X, Y, layer, and rotation position is given for each component on the PCB. These inputs are compiled into the machine programming language to drive the machine placement heads. The machine compilers also optimize the input data for the most efficient motions of the pick-and-place heads. Companies that make pick-and-place machines have videos online to advertise their capabilities. Such videos are certainly worth a few moments of time to see these amazing machines in action. 3.4. Fiducials. Fiducials are reference points that should be added to the printed circuit board during the layout phase of the PCB. By IPC standards, they consist of a distinct copper size and shape, with a relatively large clearance from all solder mask and other traces on the board. Fiducials are used by the assembly process to optically align the board for the pick-and-place machines. However, other equipment in the assembly process can take advantage of them. The overall result is the ability to move the board through assembly faster, by reducing the time it takes to align the board to the equipment. 3.5. Solder paste. Although solder paste is primarily used to provide the soldering material necessary to bond the component lead to the PCB landing, it is also an adhesive that can hold the parts in place, prior to reflow. It is a viscous mixture of solder balls of various metals, flux, and volatiles, that are activated under temperature. Flux is used to address copper oxidation issues, since copper reacts with the oxygen in the air. Though this reaction is gradual, it does create copper oxides on the surface of the copper. Solder does not adhere well to copper oxide, which will weaken the solder joint between the component lead and the board. More so, when the copper is heated, the oxidation process is accelerated to dissolve the copper oxide. Also, the flux prevents oxygen from reacting with the copper during heating, and subsequent cool down. Though most of us would define volatile as something explosive or unstable, the term is also used to describe a liquid that quickly evaporates. In this case, the rapid removal of a liquid allows for the soldering process to move quickly, thereby reducing the exposure time to high temperatures, which can impact the component functionality, and possibly shorten the life of certain components. Viscosity is a term to describe the internal friction which slows the movement of liquid. For example, maple syrup has a higher viscosity than water. Solder paste is viscous to help it stay in place until heat is applied. Solder paste can be applied to the PCB bare board by syringe, stencil, screen printed, or by automated dispensing equipment. The features of the solder paste stencils are derived from the solder paste information found in the manufacturing files, and modified by the assembler for this process. More about the generation of the solder paste files will be covered in later chapters. The solder paste is generally a thixotropic adhesive. Thixotropic materials, such as a paste or gel, are highly viscous until stressed with pressure, such as air. When stressed, its viscosity is reduced and spreads more easily. When the stress is removed, the thixotropic material returns to its original viscosity. This thixotropic property of solder paste is necessary for most pick-and-place equipment. The equipment generally uses a vacuum pen to grab the component. Upon placement, it blows the component onto the solder paste. During this activity, the pressure exerted by the airflow lessens the viscosity of the solder paste momentarily, thereby allowing the component leads to become more embedded into the paste. Keep in mind that the leads of the components are easily bent, therefore, there is a balance necessary to get the component to embed itself into the solder paste, without bending the leads, which might result in shorts or opens. 3.6. Glue dots. The purpose of an SMT adhesive is to hold the components in position. In most cases, this is accomplished by the solder paste. However, on a two-sided board, glue dots might be needed. The glue dot is an adhesive that is placed between the component packaging and the board surface, and is a permanent epoxy. It is not burned off, or removed, in any baths that are applied to the board after the soldering process is completed. It can be dispensed by syringe, or by automated dispensing equipment. The glue dot position on the PCB is generally determined by the component's centroid, which is obtained from the pick-and-place data file. The centroid is the XY coordinate that describes the center of the component. However, in situations such as a BGA package, which has leads in the center of the component, or in situations in which the belly of the component needs to be touching the landing to help dissipate heat, the glue dot can be applied to the edge or edges of the component. One may think that boards populated with SMDs on both sides would require glue dots. However, the use of the vapor phase equipment during the solder process eliminates this need, depending on the weight of the component. Glue dots are not needed for every component, and are often selectively applied. Glue dots may be used in several situations. The MELF component package type is typically cylindrical. It is risky to rely on solder paste alone as the adhesive. The practice of mixing through hole and SMD components on both sides of the board will require glue dots. Unless the design itself truly requires such a configuration, mixing through hole with SMD components on both sides of the board is a design practice which puts an additional burden on assembly and increases the cost. Through-hole components should be kept to either the top or bottom side of the board. If the PCB is to be wave soldered, a glue dot should be considered. 3.7. Adhesive curing. Prior to the actual soldering of the component to the board, the process of curing the solder paste in glue dots, if used, is performed. Curing is the process in which a material is hardened. Like any type of glue or epoxy, it is initially applied in a liquid state. The curing process hardens the material. This is done to displace gases and volatiles that could boil off during the soldering process. Failure to do so could result in displacement of the component, especially tiny devices like 0402 chipped resistors. Depending on the type of solder paste or adhesive used, adhesive curing can be at room temperature, or cured at a preheat stage of the reflow process. In addition to using flux, to prevent contamination or oxidation, the solder paste can be cured in a nitrogen atmosphere. Nitrogen boxes are commonly found in both fabrication and assembly facilities. The idea behind the use of such boxes is to lessen the other gases that may be present in the box, by constantly feeding nitrogen gas into it. Whereas oxygen is reactive to materials, nitrogen is inert. There are as many different curing techniques as there are different epoxy adhesives and solder pastes. Under most circumstances, the designer need not worry about which solder paste or glue dot formulas should be used. The assembler will handle that aspect. Special handling of the curing process will be needed if MEMS, micro-electromechanical systems, devices, or power pad devices, are incorporated into the design. A MEMS device is a micro machine with components that are microns in size, and thus more susceptible to thermal stresses. Its power pads have the ability to charge another device through close contact. 3.8. Soldering, reflow. Once the placement of all the components is complete, the entire board is run through machinery, which heats the board to a temperature hot enough to melt the solder in the paste. The temperature itself, and the duration that the board is exposed to the heat, must be maintained to a high degree of accuracy. Different materials need to be dealt with during this process, including the materials that were used in the fabrication of the board, and the wide variety of materials used in the components themselves. The solder needs to be melted, without compromising or damaging the board or the components in the process. The profile consists of controlled ramp rates and soaking periods. This reduces the threat of thermal shock, while allowing time for all components to be evenly preheated before the temperature rises to the melting point of the solder. After reflow is complete, a cool-down ramp is required. There is a balance to get the parts down to a non-degrading temperature as soon as possible while reducing the potential for thermal shock, which will oftentimes lead to cracked components. As a side note, when using exotic dielectric materials, it is important that this information is passed along to the assembler to ensure that it does not require special processes. The term exotic is commonly used to describe dielectric materials that are not typically used in the fabrication process. It is the responsibility of the designer to see to it that this communication happens, especially if a CM, contract manufacturer, is not used, or if the manufacturing of these boards is being done by different fabrication and assembly houses. If one is using common materials, such as FR4, this will not be an issue, since most houses gear their equipment to this material. A contract manufacturer is a broker who handles the manufacturing process for a company. All the design documentation is provided to the broker, who will contract the design to the appropriate fabrication and assembler, in addition to handling the handoff between them. They may also handle the procurement of the components that are necessary. It is rare to find a manufacturer who handles both the fabrication and assembly of the printed circuit boards. More so, be aware of overseas manufacturing houses that can perform both fabrication and assembly. A promising design can easily be copied. There are generally 4 stages, or zones, to the temperature profiling in the reflow process. Preheat: the temperature is raised steadily, over a period of time. Soak: the temperature is leveled off for a duration of time. This allows the heat to warm up the entire board and all components to a consistent temperature. This is to avoid having temperature differentials, which can damage the board or the components. Reflow: the board temperature is raised to the solder melting temperature. This is done for a short period of time to avoid applying any more heat than necessary. The fastest way to reduce a component's lifespan is to apply heat to it. Cooling: the temperature is steadily lowered before the board is exited from the reflow oven, to prevent thermal shock by cooling too quickly. This heat profile ensures the devices are not subject to rapid temperature changes that could crack and damage the devices. Also, heat profiling allows outgassing of liquids and volatiles in the glue dots, if used, and solder paste, to prevent displacement of the devices. A common defect is tombstoning, in which small passive SMDs are lifted or skewed at one end, caused by oversized mounting pads, too much solder paste on solder pads, and high viscosity of the solder paste. The most common cause is the uneven heating where one pad melts, creating surface tension before the other pad melts. Some of the reasons for tombstoning have to do with earlier stages of the assembly process, although the defect takes place during the soldering process. There are several means of heating the PCB board, but most common are the non-focused IR, infrared, panels, and vapor phase heating. There are advantages and disadvantages to both types. Non-focused IR panels are just that, they simply provide heat into the chamber. They are better at providing a constant temperature within a zone, and generally are easier to profile. However, as the board moves into a different zone, it will be subjected to a sharper temperature rise. Thus, the IR panel process requires a longer soak time. In addition, the process requires longer peak times for the soldering, which, as mentioned earlier, prematurely ages components. 3.9. Vapor phase. The vapor phase method allows the board to be heated more evenly, at a more rapid pace. However, this in turn makes it more difficult to control the temperature profiling. Vapor phase has been around since the 1970s. It fell out of use in the late 1980s, as other convection methods became more popular. However, with innovations in the vapor phase equipment, the growing use of SMDs, and the levying of RoHS, reduction of hazardous substances, to remove lead content from electronics, vapor phase is now commonly used. Vapor phase uses condensation, which is a very efficient way to transfer heat, second to direct contact to a heating element, which is not practical during the soldering process. As a side note, the other forms of transferring heat are radiation and convection. Because of the efficiency by using condensation, the temperatures can be kept lower, for a short duration. During the process, an inert chemical known as Galden is brought to a vapor state, 230 degrees Celsius. Though in a vapor state, the weight of the Galden vapor prevents it from escaping into the air. More so, it forms a definitive layer. The board is initially brought to the surface of the vapor layer for preheating, and then completely submerged for reflow stage. The vapor completely covers the board, preventing any air contamination. After the solder has melted, the board is raised above the vapor. The Galden evaporates quickly after the board is brought to a colder temperature zone. 3.10. Soldering, wave. Over the years, components have not only become smaller, but there are more types of SMDs being used than ever before, and many with specific assembly requirements. Solutions to these ever-increasing challenges demand well-controlled solder techniques. Even with these new demands, the venerable wave, or flow, soldering technique, is still a viable process. This technique was used many years for soldering the through-hole parts on the bottom side of the PCB. The PCB is passed over a bath of liquid, melted, solder, in which the solder machine creates a standing wave in the flow of the solder bath. The peak of this wave of solder just touches the bottom side of the PCB, thus soldering all the exposed pins to the PCB at the same time. Wave soldering must be very carefully controlled when both through-hole and SMD devices are present on the board. Prior to wave soldering, the SMDs must be mounted with a sturdy adhesive. If the adhesive is too thick, solder voids under the device pads can occur. Other issues can occur as well. Shadowing of one device by another can cause solder voids, and the eddy currents caused by the shadowing device can cause excessive solder bridging between device pins. 3.11. Hand soldering. Hand soldering is not an efficient process when assembling boards, especially those with SMD components. It can be done, however, given the size of the typical SMD components. One would require a microscope, a pair of tweezers in one hand, a soldering iron in the other, and being very steady in both. Even if pick-and-place machines are used for assembly, keep in mind when designing a PCB, that testing in the lab and rework may require significant hand removal and replacement of components. Just because a smaller component can be used, doesn't always mean that it should be used, especially with capacitors. 3.12. Cleaning. As the PCB progresses through the assembly process, the board will be cleaned multiple times. Prior to soldering, the board must be cleaned of organics, fingerprints, oxides, and other soils, to ensure a clean solder base. After soldering, the board is cleaned of residual flux and solder particulates, which can corrode the metal on the components and board over time, reducing the life of the board. Cleaning chemical solutions and techniques are continually changing to meet the newer solder formulations. These newer formulations are primarily in response to RoHS. Prior to RoHS, the most commonly used solder was a 60-40 mix of lead and tin, respectively. In 2002, the European Economic Community adopted RoHS to remove the lead content in electronics. It was put into effect in July 2006. As a result, component manufacturers had to modify equipment to handle the lead-free solder formulas. The United States has not adopted RoHS as law, except for the state of California. However, China, which is a worldwide producer of electronic components, adopted RoHS. Given the global nature of the electronics market, all electronics companies in the US have adopted RoHS to sell their products globally. To meet these challenges, newer chemicals and techniques are always emerging, but the fact remains, the PCB must be cleaned, and the parameters defining the cleaning process must be thoroughly understood by the assembly house. As the designer, you can improve the impact of the cleaning by being strategic about device spacing, device alignments, device selections, and cautious silk screen usage. Here is a partial list of the considerations made by the assembler when choosing the optimal cleaning method for a given board. What are the contaminants sources? What cleaning solutions will best remove contaminants? Will the solutions require board agitation? Is a vapor phase degreaser the best method? Is a chemical solution and ultrasonic the best cleaning solution? What is required to remove the remaining cleaning solution? Are there any devices that may be damaged with the selected cleaning technique? What is the size and shape of the PCB and mounted components? If the PCB requires a conformal coating, the last cleaning step should leave the PCB clean and dry, with no residue that prevents the conformal coating from sealing the PCB. Conformal coating is a coating that is applied to both the board and the components, to seal it against moisture and chemical contaminants. It is applied to boards that will be exposed to harsh environments. 3.13. Inspection. Visual inspection is performed to detect defects or damage to the board and components throughout the entire assembly process. In fact, the very first step in the assembly process is to inspect the bare boards from the fabrication house upon arrival. This is a visual inspection performed by a technician. There may be other tests performed on the boards upon arrival. The topic regarding testing will be covered separately. Some of the damage will be obvious, such as damage caused by inadequate shipping packaging, and rough handling during shipment between the fabrication house and the assembly house. Some of the defects are not as apparent, thus the need to carefully inspect the board. Some of these issues include warpage. Board warpage is a concern, especially if surface mount components are being used. The assembly processes requiring the application of heat at varying temperatures may introduce warpage all on its own. Therefore, starting with a board that already has deformities will only exacerbate the problem. Measling. Measling is a condition where the glass fibers and resin of the dielectric are separated. It appears as white cloudy spots under the surface of the PCB. There is still some controversy as to how serious measling is to the reliability of the board. In general, the consensus appears to be that if the measling is not too widespread, and the spots are not too large, the measling can be accepted. Large measling spots can point to possible delamination, which is not acceptable. Large measling spots can also create impedance discontinuities for high-speed signals. Wide gaps in the weave of the fiber fabric can cause impedance problems for high-frequency signals. Delamination. Delamination is the separation of copper and dielectric materials. It can be caused by improper curing of the prepreg epoxy, or caused by moisture between the layers of the PCB. There are several ways in which moisture can get into the board during fabrication. For example, it could be left behind in the PCB during one of the wash and dry operations. It can also enter through a cracked via barrel during a wash operation. Delamination can also be caused by material outgassing due to excessive temperatures during one of the cure cycles. It can be seen as a large spot under the surface of the PCB, and in some cases, looks like a blister on the surface. Copper damage. Copper features such as S&D mounting pads, vias, through-hole mounting pads, and traces, are inspected for damage and defects. Silkscreen smearing. The smearing of the silkscreen overlays will result in rejection of the incoming PCB, especially if the silkscreen found its way onto any of the copper landing pads. As the PCB proceeds through assembly, there will be additional inspections for correct component placement, amounts of solder paste on the board, and the pre-cure state of the solder paste and adhesives. After component placement, the alignment will be inspected. Most of the time, these inspections will be performed via automated video inspection systems. Many assembly houses use sensitive instruments to measure the flux contaminants in the wash solutions. They can detect flux residue down to the ppm, parts per million, levels. This method is very useful when visual inspection is not possible, especially under component packages such as the ball grid array and leadless chip carrier. To detect poor solder connections and solder voids under these parts, X-ray can be used. Usually, the assembly house will not X-ray every device on every PCB, rather they will spot check multiple boards. If they find problems, they will increase the inspection criteria, and review the assembly process. Visual inspection can be made easier depending on the accommodations that are made within the PCB design itself. One accommodation that is of great assistance to the assembly process is known as a visual accommodation. We must keep in mind that the technician performing the visual inspection is looking down at the board. Therefore, a quick rule of thumb for the PCB designer is to place the components such that a visual path of at least 45 degrees is available. This is not a hard and fast rule. For example, if a large radial capacitor is mounted in line of sight, it would require an area approximately 2 square inches of clearance to get a 45-degree visual path. Obviously, that is not realistic. In this case, the technician must rotate the board to look around the capacitor. 3.14. Assembly cost. This is the cost of having the components purchased, and boards populated with components. It's very rare for assemblers to place SMT components by hand, especially due to the microscopic size of most components. Automated pick and place equipment is used for this operation. One of the fastest ways to add cost to the assembly process is to mix surface mount components with through-hole. While this cannot always be avoided due to the connector types, it should be minimized as much as possible. If one is trying to save a buck by using a through-hole component rather than an SMT equivalent, the cost saved on the part will be lost by the increased cost of adding additional assembly processes. The equipment or labor necessary to insert and solder through-hole components is different from the equipment that can handle surface-mounted components. The bill of materials can have a substantial impact on cost and time, depending on the components being used, and the quantity of the components. Respin is the process in which the existing boards are scrapped due to design flaws. This requires changes in the PCB layout, and will require a new run of the manufacturing process. With each run, costs are incurred for fabrication, assembly, and bill of materials. 3.15. Chapter Summary. As an overview of PCB assembly, we discussed general process flow. However, we must caution that the sequence as presented is far more involved than we described. From incoming inspection to packaging for shipment, the individual tasks may be repeated numerous times, not necessarily in a linear order. Adhesive dispensing is the placement of either a glue dot or solder paste to hold the mounted device until adhesive cure or soldering. Accurate pick and place files are required to automate the device placement. Adhesive curing is often called pre-cure. It's used to increase the viscosity of the glue or solder before reflow soldering or wave soldering. Soldering demands a clean board, free of contaminants and oxidation. The soldering profiles are the temperature zones the PCB will be subjected to, in order to reflow the solder, without displacing the components to be soldered. The profiles are further defined by the selected solder paste. Gerber solder paste files control where the solder paste is to be dispensed. Cleaning takes place at multiple sequences of the assembly process. Cleaning must be well controlled to make a reliable PCB. To ensure control of the assembly process, good inspection techniques are demanded throughout the assembly process. Good inspection techniques start with the PCB designer, and the proper placement of components to support the ability to make good inspections.